Hey there, amazing people. Welcome back to my channel AI Connect Grow. It's so great to have you here. And if you're new here, hi, I'm Kalpa and I am thrilled to have you join the AI journey. Today, we are diving into something super exciting: Transformers. You have probably heard the buzz, right? Transformers are the backbone of all those cool AI systems, from language models to chatbots and beyond. In this video, I'm going to break it down step by step, ensuring each concept is clear and easy to follow so you can confidently grasp the foundations of Transformers and build cool GenAI applications. I'll be starting with foundations of Transformers, input embedding, followed by positional encoding, and we'll move on to multi-ed attention, which is one of the super important concepts in Transformers. And we'll also include feed-forward neural networks, and we'll wrap it all up with softmax. I'll be creating series of videos for each one of these components separately, wherein I'll be including theoretical explanation, PyTorch implementation, and will also share you the blog as well so that you can revise during your leisure time. If you're wondering that you're not aware of PyTorch, please don't worry. If you know Python or Java or any other programming language, it is going to be super easy for you. So if you want to be an AI expert, please subscribe to my channel and support me. Your support means the world to me, and this will help me in creating even better videos for you. So without any delay, let's dive into our today's topic: Transformers. So, what are Transformers? Transformers are a state-of-the-art architecture that's revolutionizing the field of natural language processing. It was introduced in the year 2017 in the paper called Attention is All You Need. The transformer architecture is the basis for most of the recent well-known models like BERT, GPT, Gemini, and Llama models, etc. Researchers have not only applied transformer architecture for natural language processing, but they are also using it for computer vision and reinforcement learning. Therefore, understanding the transformer architecture is crucial if you want to know where machine learning is heading. If you go to my website aiconnectgrow.com and click on blog, you will be able to find all my blogs over here. This is the blog that I've written on Transformers, and you can use this as a reading or a revision material once you're done watching my video. Now, as a first step, let's try to understand the structure of transformer architecture. Unlike traditional models like recurrent neural networks, which process input sequences sequentially, the key advantage of transformer is parallel processing. This enables them to handle long range dependencies and solve problems like exploding gradient and vanishing gradient that we were facing in recurrent neural networks. Another key component of the transformer is the attention mechanism, which allows the model to focus on different parts of the input sequence when producing each word of the output sequence. This makes transformers highly suitable for a wide range of tasks, from language translation and text generation to image processing and beyond. With this being said, let's understand the different components of transformer architecture. The initial component of transformer architecture is input embedding layer. The inputs are tokenized into words or subwords and then being fed to input embedding layer. Here in this layer, the words are represented in a high dimensional vector so that it learns the context between the words. Once we get the high dimensional vector for each of these tokens, then it is being concatenated with positional encoding. So positional encoding makes use of sine and cosine waves in order to understand the order of input sequences. Since the transformers process the data parallelly as we discussed earlier, it doesn't know the order of words. So in order to add the order of words to the input sequence, we concatenate the input dimensional vectors with the positional encoding vectors. And it is being fed to encoder block. The encoder's role is to process the input sequence and create rich context-aware representations of it. This is achieved through a stack of N encoder blocks. If you see, each encoder block has several components within it. The main component, as we discussed earlier, is self-attention mechanism, followed by normalization layer, and then which is being fed to feed-forward neural network, and normalization is applied again. So at a high level, self-attention mechanism allows the encoder to focus on different parts of the input sequences simultaneously. For example, while processing a word, the model can pay attention to related words anywhere in the sentence. It computes weighted representations of all tokens relative to each other. Now that we have seen different parts of encoder block and understood that it is used for processing and transforming the input sequence into higher level representation using self-attention and feed-forward layers. Its purpose is to capture the relationships and features within the input data. Some of the models only make use of the encoder block. For example, BERT, which is primarily an encoder based model, which is used to understand the contextual representation of the input text. And this can be fine tuned for specific tasks like classification, question answering, or named entity recognition. Now that we have covered input embedding, positional encoding, and encoder blocks at a very high level, now let's understand about the decoder block. Similar to encoder block, decoder block also has masked self-attention. Why is it called masked self-attention? Because it ensures that the model only attends to the previous tokens in the targeted sequence. This is crucial for autoregressive tasks like text generation. Then it is being followed by cross-attention mechanism. This layer connects the decoder block to the encoder. It uses the encoder's output to focus on relevant parts of the input sequence while generating the output tokens. This ensures the generated text is contextually aligned with the input, followed by feed-forward neural network and normalization layers. And then finally, the output tokens are generated one by using softmax layer that predicts the next token based on probabilities. At a very high level, we have understood now that encoder is used to encode the inputs into contextual representation, whereas decoder is used to generate the output sequence step by step. Now that we have understood transformer architecture at a very high level, this video will be followed by a series of videos explaining each one of these components individually. And I'll be sharing you PyTorch code to show you the input and output from each of these layers to make your understanding of transformer architecture very strong, which will help you in building GenAI applications. With that being said, I'll wrap up for today. Have a good day.